Then, so now today is chapter number 5. Well, it's a Z transform. We will be brief with its properties. We first define it, what it is, actually just a simple formula. And you will notice that it is basically the same as Fourier transform, only that our Z variable is a complex variable. So we can think of the Z transform as a generalized Fourier transform, actually, to explain things more simplistically. And then what our goal in this chapter is that we will be working with these partial fraction expansion. So this is back to the maths of your first year of study. I believe you should have had some kind of this at your maths courses. And now it's time for us to recall this tool and to use it, because we will need it when we design our digital filters. As we will see later in the coming chapters, that we still have that you have some long fraction, and you need to cut it into smaller parts so that you can apply the Z transform from the lookup table, and that's the standard procedure. So basically, we will be working on this partial fraction expansion, and I will then tell you the number of the homework that I would suggest for you to practice, just to make sure that you get that you got the material right after you read this chapter. And then in blue color, as usual, I try to give a hint. What is the basic thing from this chapter? So I will be happy if you know how to apply this Z transform to solve linear difference equation, because we know that we can solve the difference equation in the time domain without applying any transforms. So there's one way of doing that, and this is an alternative way. Alternative way is that we have a difference equation as the input, we transform it to the Z domain, and we solve it there, and then we convert back from Z domain to the time domain. So basically, you do it in an alternative domain, and there are procedures for that. And actually, in order to do this, solution of difference equation, you will need to use partial fraction expansion. So we will have examples, and you will see what is meant behind these lines here. Okay, so let me just first show you the definition. Well, this is a text, but we have this formula here. That's the formula how we define the Z transform. So this is, you have your signal, x as a function of n, where n is our time index, right? Sample number, in other words. We have our signal. We need to multiply it by this z raised to the power of minus n. And we have a loop. We loop from 0 to up to some number. Well, in theory, this is infinity, but in practice, of course, we have some limit, some finite number, some particular number that you have to use. And then you have to loop through this cycle here, multiplying your signal by this function. And z is a complex variable, so it has a real part and it has imaginary part. And now, if we expand this expression, we will have just this addition of products, x times z plus x times z. So only you have to be careful with the indexes. If this is 2, then this is minus 2. It's quite simple, actually. Okay. And here's the example. For instance, imagine our input signal is a unit step, a familiar test signal, unit step. So it is 0 up to 0.0 in time, and then when n is equal to 0, it jumps to 1 and stays there. So just as we call it step, unit step, right? We need to find the Z transform of this input signal. Okay, so it's a quite simple solution. You have this definition. This is definition of the Z transform. Only instead of any input x, you substitute your particular input, which is unit step, u as a function of n. Then one more thing here, we can replace this by simply you can rearrange things here, right? You can write z raised to the power of -1, and then everything is raised to the power of n, which is the same, equivalent, because un is simply, as I said, ones, right? So it's, imagine you still have 1 here in front. And when you expand this, 0 raised z raised to the power of n will be, of course, 1. If you substitute 0 here, right? If you substitute 1, when we have 0 raised to the power of -1, and basically this means that we have an infinite geometric series. This thing is called infinite geometric series, and from the theory of geometric series, we know that we can have a closed form solution for this, and no matter how many terms are there, you can find the solution as this. This is just taken from the maths. Provided one condition, that the thing which is in the brackets here, its absolute value should be less than 1, right? It must be a fraction. Otherwise, this series will not converge. It will go to infinity, and we want it to converge. So in that case, and that's a solution. So we found the Z transform of the input signal, which is this, provided the Z variable satisfies this condition. Do you have any questions at this point?
No, not yet.
No, it should be plain here, right? So basically, I believe you had something from this mathematics courses about geometric series. This goes back to our early days when we were studying math, right? So here we just repeat things. Now another example will be one step higher. So instead of unit step, we have unit step multiplied by this, which is exponential function. This is quite a frequent signal in our theory, that we have a signal which decays exponentially. If this a is a fraction, which usually must be a fraction, otherwise the signal will go exponentially to infinity. We don't want that, because we cannot handle these situations. So usually a is assumed to be a fraction, so it's a number less than unity. And then this is when we recognize this expression as an exponential signal. And this is a very frequent signal that we encounter in our course. Again, we need to find the Z transform of this input signal. We substitute expression here into the definition of the formula of the Z transform. Now we have a raised to the power, a times Z raised to the power of -1. And then we expand it. And of course, this time we have not 1, but we have a in front of each term involving z. So it means that this a will pop up now here at the denominator. So we have one modification compared with this one. Here we had 1, by the formula told us, and now we have any number which could be other than 1, just the number a. So just a simple modification. And then we won't be doing all this because people already done these procedures for us. And this is this lookup table. We just need to use this table whenever we get any signal. So look at this. We have standard signals, like our familiar example of delta function, delta impulse. Observe that its Z transform is just 1. You apply a unit impulse, and its transform is 1. You apply unit step, you get this. And we already covered this example at the beginning, only we have in front some number a, and this number a will appear here as well. So basically it's the same unit step scaled to some a value, right? Then if you have something like this, if you have n multiplied, which stands as usual for, as always for time index, n multiplied by unit step, then its Z transform will be this. Now, the idea is that we will need this table whenever we have to do the partial fraction expansion. So your goal will be to cut a complicated fraction into smaller pieces and these pieces should look similar, should have the same shape as some of these members from the table. And then you have to go back from Z domain to the time domain and convert from, for instance, if you find that you have a term like this, you will know that its inverse transform, Z transform, will be this term here. Okay, so we will see now examples shortly that using this table, we will be jumping to this table and referring to it many times here. And this table is split into two parts because I couldn't fit them all on one slide, because otherwise the font will be too small. Okay. This example, I believe, was a series of examples. Okay, it tells you more complicated cases. I don't think we will go through them all here. You can, I believe you can do it at home when you have more time to study carefully how these things get solved here, right? For instance, let's pick something which is more interesting. For instance, part B. Imagine that our input sequence, our signal, is the sinusoidal function, which has the amplitude of 10 units, and then the frequency is the angle frequency is 0.25 pi, right? This is our frequency. So the solution here is very simple. We are referred to our table, line number 9, and this is it, right? We observe that our particular sequence has the shape of this, which corresponds to line number 9 from the table, right? Then it means that our Z transform will have the shape of this, where A will be the same as this one. So the number which stands here will pop up here at the numerator and denominator. And that's what we have here. Sorry, I skipped already, probably. Yeah, that was this one, right? Okay, so we have 10 now. Our amplitude is 10, right? And our signal is sinus 0.25 pi n. So now these numbers pop up in the formula, and cosinus as well. So you simply have to commute between the table and this to verify that we are actually doing the right thing. And then that's a matter of making some arithmetic to reduce things. So you then multiply 0.25 by 3.14, which is just the same as pi, and you get, and multiply by 10, and you got this number. So you should simply make arithmetics. That's it here. Well, these are quite simple things, okay? So I believe I don't need to comment on these very long, because time is precious here for us. I want us to quicker to get back to get to the point where we need to make this partial fraction expansion, okay? And this calls for this inverse Z transform. So when we do this partial fraction expansion, we have to do the opposite thing. We have the Z transform, and we have to go back to the time domain. And so the inverse Z transform is denoted using this Z raised to the power of -1. -1 means that we are making a reverse transformation or inverse transformation, right? Here we have a few examples. For instance, let's do the first one, A. We have, imagine we are given already a Z transform which consists of 3 terms. The first term is a constant 2, and the others are like this. We have to do the opposite transformation. We have to make to find what is our signal. What is the signal as a function of time n? Okay, we have to look at the table. Since we know that, okay, this is slide number 11. I have to go back to our table. It's very inconvenient because I have to jump between those. Here, look at line number 2. 2 means that basically you have 1, multiplied by 2, right? Very simple. So 2 is a constant and 1 has a special meaning. You convert 1 to delta function. So if you have 2, it means you have 2 deltas. So your signal is 2 deltas for this one, right? And that's what we do there. I go back to 11. So I have two deltas, right? Now here, observe, in the first example at the very beginning, we had, if you recall, z multiplied by z minus 1 corresponds to unit step, un, and it's still multiplied by 4, so we have to rewrite this 4 here. So we have 4 unit steps. This term corresponds to 4 unit steps. And these two look like very similar, only instead of 1, we have a value of 0.5. As long as you have some number other than 1, it means you have a series, you have a number raised to the power of n here. And this number is 0.5 in this particular case. Of course, we have a minus in front because the minus was here, times unit step, because that's the standard thing for this function, okay? Okay, that's the way it goes, okay? And then we are given, yeah, that's the thing we want to do here. This is the procedure, the algorithm consisting of 4 steps to do the partial fraction expansion using our lookup table. So now we will go carefully through this procedure using examples and see if we are able to understand what's going on there. So we have, we will be using these formulas, and probably this might be the most challenging part to understand, that you have 3 cases. When we solve our equations, we will see that, remember when we have a square root, we have a square equation. When you have to solve it, you have roots. These roots can be real numbers or they can be complex numbers. So depending on your solution, we will have to use different procedures. And in this table, we have these templates, how we do that. Okay, we will make first, we will make an solve example using the most simple case when the roots are real numbers, not complex numbers, and then it should be easier to catch the idea of the complex numbers after you got the idea with a real number. Okay, let's go to the point. This is the first example that we have to do our partial fraction expansion. So here we are given a fraction which consists of two terms at the denominator, right? So we have, whenever you have something like this, we know that we have to split it into smaller parts, because if you look at our lookup table, we don't have a readily available solution for this. We have to cut it into pieces that have entries in the table, right? It means we have to proceed like this. So first of all, if you look at this algorithm, number 1 is eliminate negative powers of z. Get rid of those. See, we have z raised to the power of -1 and here as well. So since -1 and -1, so the easiest thing to do is multiply everything by z squared, numerator and denominator, z squared, z squared. After you cross multiply this, you will get rid of the negative powers, right? So z squared will stay, of course, at the numerator. And then this z goes to z times 1 is z, and then z times z minus 1 is simply 1, right? So we just get this multiplication. So we borrow one z for these brackets and another z for these brackets, and then this way we get rid of negative powers here. So we just simply did the first step, okay? We did the first step here. Then the second step looks, if you read this text, this looks quite frightening, but if you look at the example, actually it simply means what you have to do in second step. You have to get the fraction on the left-hand side. So here you have x as a function of z. The standard form requires you to have this divided by z. So you always have to have something like this on the left-hand side. It means you have to borrow 1z from this fraction, right? So that's why we have now not z squared, but simply z raised to the power of 1, because another z went to the denominator here. So if you cross multiply these, you see that this is the same, right? So now this is the form that you have to use, okay? Here, this is. You have to determine the rational function, it's said in mathematical jargon. Next, what we do here. Now that's the idea. We want to split it into two parts. And we have to determine the constants a and b. At the time being, we write them just like that because we don't know what they are. We need to find them. And finding the constants is using the recipe here. Since our poles, these are called poles, by the way. The roots, if you have a polynomial in the denominator, so this corresponds to the poles, a special name for that, right? And we have these as real numbers. See, this was 1 and 0.5. So these are real numbers, not complex numbers. So that's why we can use the case number 1 here, the simplest case. Okay, we're using this table. Okay, so now this is the nice thing goes about that. You have to be careful how we do that. Imagine you want to find the constant a. So you write the term which is below it in front here. You multiply it by the thing from the left-hand side of the equation. So you have to map things here. And when you do this at your homework, you also apply the same procedure. So you have just to study it carefully how it is done in these examples, and then do the same stuff for your homework. You put this one here, you put this one here. You place the line, meaning that we're taking the particular case when z is equal to 1, because this is the number 1 here. And minus, ignore the minus. Minus belongs to the formula. So your number is 1 here, okay? Your number is 1. And it is equal to, now you write the fraction which is the opposing one. So this one was here. Now you take the fraction, z minus 0.5. The z, by the way, it's very complicated, gets from here. So you take this one from here, and it appears, shows up again here then. So, okay. So we'll imagine you have to use all the pieces. You already have used this one, then you have used this one. Now you have to use those two. So they all should be used here. So now we're using these two here. Okay. Again, the line z minus z equal to 1 is the same value. Now it's time to substitute the 1.
Excuse me.
Yeah.
Why in the second part the z equals 1 if we have 0.5 above? Because we take 1 from the equation above, right? Where we have z minus 1 in the first part. Where's a? Oh, okay. Never mind.
Yeah. No, that's it. Look, this is just we're doing the right thing. Now we are substituting this value of 1 into the formula. Okay. So 1 will be here, right? 1, and 1 will be here as well. So 1 divided by 0.5 with 1 minus 0.5 will be 0.5, and 1 divided by 0.5 is 2, right? So we simply substitute 1 for these two z values here. And you pops up this number 2. Now, with the B part, you do exactly the same, only in the reverse sequence. Now, you take Z minus 0.5 in front because it belongs to the same fraction, right? Then this goes as before to the right. Now we place the line, and now it's 0.5. And then, because of that, you take the opposite fraction here now, and 0.5 again. So that's the trick. You have simply to replicate the procedure, right? Okay. So in case you wonder why it is so, well, I think you have to go to the textbooks that explain maths more thoroughly, because our textbook is basically used for the applied things. No, we don't do derivations in this textbook. So if you wonder why this procedure is this way, I suggest you go to some math reference on maths, where we show derivations and explain why this is done this way. We simply have a recipe, and I will be happy if you know how to use this recipe, just following the pattern, and that's it. Okay. And once you got these numbers, 2 and minus 1, now you put 2 instead of A and minus 1 instead of B. That's it, right?
I got a question.
Okay.
So for understanding, right, when you find the constants, how do you interpret that Z equals 1, right? Because when you put Z equals 1 at the start, oh wait, okay. So for A, for example, right?
Yeah.
Z minus 1 times when Z equals 1, when you like substitute the Z as 1, you get 0, and then you end up with
No, don't do that. Don't substitute anything at this part. Substitute it only here. This is just the template to derive to get to this point here. Substitution is only done at this part here. Because if you try to substitute 1 here, you will of course get division by 0. It's not our intention, right?
Okay.
Well, you have to realize, imagine that you make equation. These parts should be, because basically it's the same equation, right? This is an equation. And this, what you see here, it's the same equation rewritten other way, right? Just pay attention. You multiply this one by this one, right? And it should be equal, it should be the same as this part, right? So basically you rewrite the same equation the other way around, but substitution is done only at this part here. And then you don't have divisions by 0. We can get the normal numbers. I'm not sure if I explained to you this point. Still confusion about that?
Yeah, because it doesn't really make sense if it's like this equation, because I'm doing it right now, like trying to substitute. I mean, like toss those, I guess, numbers around, but still, like when you put, for example, that part with B divided by Z minus 0.5 to the other side, right? You get XZ divided by Z minus B divided by Z minus 0.5, and you multiply by Z minus 1, but both of those parts are multiplied by Z minus 1. So if you substitute, I mean.
Okay, but look, but if you get to this point here, I mean, everything makes sense then, right?
I mean, if I skip everything else and just like ignore everything that's like that's a gap inside my head, then I mean, I guess I could like take it as for granted, I suppose.
Well, I guess we should go to some maths references then. There should be some explanation why they do things like that. I couldn't, honestly, I don't even know why they're using this procedure. But it's a classical procedure. It is like that, and well, things actually work this way, but I don't know why the derivation is maybe could be a bit bizarre. I don't know.
Yeah, it's a bit bizarre.
Yeah, so well, if we forget, and I mean something, as we say, if you don't understand things, but if you can believe in those things, these things still work, right? if we really yeah.
But it's hard, it's ununderstandable.
Okay, well, maybe I will give you my if I see that students are interested in these details, I maybe give some thought at home, and maybe I will get the answer then. Why so that it shouldn't be some magic. It's of course things are explainable here. It should be some logic, but at the moment I don't know what is going on here at this part. Well, I only follow the procedure. I get to this part, and then it makes sense. But here, yeah, I agree with you. But if you look at this, if you place 1 in here at this part, you have division by 0, so you cannot do anything, right? Okay, let's not dwell on that, because we will not go anywhere. Okay, our goal is to get to the answer, and then suppose we already went through this. Now, what's here? We need to go back to our algorithm. Well, of course, in step number 2, we divided our function x, z by z to obtain the partial fraction expansion, to perform partial fraction expansion. Now, of course, our goal is to go back. We don't need this. We need x, z again. So we have now to do the opposite. We have to multiply both sides of the equation to revert to the original shape, the original form, right? And that's what we do now. We multiply everything by z to get rid of this, and so that we only have x, z on the left-hand side. Then of course z appears here and z appears here. Right? And this is now the last step remaining to do, is to use our table 5.1, right? To do the opposite. And we recognize that this is what? This is our unit step multiplied by 2, right? Our unit step multiplied by 2, and this is exactly the same, only that instead of unit step we have a exponential function 0.5 raised to power of n, right? Here. So our familiar terms already from the previous examples, and just to have it more fun, we have also a table. You can substitute particular values of n like 0, 1, 2 into the formula to get the output. So, of course, 2 raised unit step is always 1, right? So it will be always constant 2 minus something. And instead, if you place n for 0, so 0.5 raised to the power of 0 will be 1. So that's why 2 minus 1 will make it 1. So we just confirm the calculations. And of course, if you take the infinity, if you place infinity instead of n, so fraction raised to the power of infinity will be, and of course this is it will turn to 0, because right we raise in a fraction to a very large number. It will gradually turn to 0. So basically our final solution will go to 2, because this is the part which never changes. 2 times 1, 2 times 1. Okay. Okay, so I believe this example was clear. Well, apart from this thing that we agreed here, this is a tricky part, right? If we ignore for the time being this, then the procedure is quite straightforward. Well, another example from the textbook is a more involved one. Now, this is what happens if we have the situation of complex roots, right? It could be, for instance, you have a square equation like this. If you try to solve it, you will have the square root, and then you will have a negative number below it. It means that you cannot solve it without using complex numbers with imaginary parts, right? So then we will have to use a more complicated procedure, unfortunately. and we will have to deal with complex numbers, to do some arithmetics with complex numbers, which for some people is a nightmare in itself, I know. Well, I suggest we skip this for the time being, because you might be already dizzy with these things. And let's move forward. So assuming that we only have cases when you have only real roots, without complications with the complex roots, okay? So let's skip this part for the time being and go to the end of the presentation, and then we can come back to this complex root case. Okay, this is a reminder. Yeah, and repeated pulse, one more case. Okay, this is a help for you, right? We have our MATLAB, a very good friend. This very useful function residue. So you can actually do the expansion applying MATLAB. For instance, let's look at this example. I believe we had this already. We did it by hand. Now we can check, you know, if I'm not mistaken, or at least it looked very similar to this one. So we can now we can check it using MATLAB. So first of all, there's a function conv, which allows you to, suppose you're lazy to cross multiply these two terms. So you simply put the coefficients. So you write conv. The first vector will be coefficients corresponding to this. So 1 and -1. So if you had some other power of z, then another number would show up next to that. So, but now we have 1 and -1, comma, another brackets correspond to another term, another vector, 1 and -0.5, right? These are coefficients. So you do this function. So it multiplies numbers for you, and that's the result. So you have the same as 1 -1.5 and 0.5 of a plus. So it's a square equation, right? 0 power, 1 power, and square power. You map these numbers, right? So basically, this function conv does simple multiplication for you. It doesn't look like a big deal, of course. We could have done this by hand, but just know that you can do this using MATLAB. Okay. Of course,
Sorry,
if you want.
stupid question.
Right.
So, was convolution just basically multiplying brackets?
Well, no. Convolution is actually a more involved thing, as we know, right? So, but here in this particular case, it allows you to do this multiplication just as a imagine. Its convolution is a technique which we use for digital filters, which it's more involved, right? But in this particular case, you can use it to do the multiplication, right? So basically, you're using a heavy tool for some simple task, so to say. Yeah, you can use it. Sometimes we use a machine gun to shoot something what we don't have. We could use just a simple pistol here, right? So that's the case. Okay, but that's not our goal. Our goal is to come to this, because now after we do the first step, we prepare our fraction for the standard template, right? We still need to do manual things. See, we still have negative powers here. So the same thing goes as before. We have to get rid of negative powers of z. So we multiply everything by the highest power. And the highest power here is -2. It means we need z squared. And then at the numerator and z squared at the denominator. This way we get rid of negative powers. We turn into positive powers, right? So then, remember, we have to obtain the function as a fraction. So now we have to divide xz by z. So it means that we will lose square here, right? Here. Now instead of z squared, we get simply z, because now we have a fraction. This way, again, we are ready to use the residue command in MATLAB. So the first vector corresponds to the thing in the numerator. The numerator we have 1 is our z raised to the power of 1. So we have a coefficient 1 because no number is in front. So 1, right? And we write 0 for the constant term because otherwise, imagine you would have something like plus 0.2, for instance, or minus 0.3, a constant term, or in other words, z raised to the power of 0. But here, since you don't have anything next to z, meaning that we have a constant term is 0. So you place a 0. So this is our numerator. And the other thing is the vector of denominator. We already had this one. We take it from here, from convolution, right? We take it from convolution and put it here, the same numbers. Do the residual command, you get 2 minus 1. Remember these numbers that we did before? Here, these are the same numbers. So we didn't do MATLAB did it for us, okay? Here, 2 minus 1, and poles are 1 and 0, 5. So now we write the answer. 2 goes here, minus 1 goes here. We have poles. Pole means that we have z minus all this in the formula. So you always write z minus 1 or z minus 0.5. And you get exactly the same solution as we did by hand, right? Ignore the k for the time being. There is another part because it's called RPK. So it's another term. If you are using in some particular cases, you might have something not as an empty vector as here, but some numbers. In our case, I will always give you examples, problems to solve with most straightforward cases when you will not get anything in here. So it will be an empty term. So basically, you don't need to think about that. I don't want to make things too complicated for you.
Sir, in B, you said z minus 1. Why not z plus 1? Or why not z plus 0.5?
Okay, because this minus belongs to the, imagine like this. I don't know how it is explained in mathematical textbooks, but my explanation from my internal explanation is for me to recall, minus belongs to the formula, right? It's always there. So if you have 1, you place 1, 0.5. If you have minus here, imagine, minus, if we had minus 0.5, then minus and minus makes it a plus. In that case, we would have a plus here.
Okay, thanks.
So just yeah, I know it's confusing. So sometimes it's tempting to use, I mean, to think that this minus belongs to the number, but actually it's not. So the minus is basically, it's hardwired into the formula, okay? And these numbers are just what comes here.
Okay, thank you.
Yeah. So if you recall this rule, so you should be safe. That's what I do at least, okay? Because
Yes.
I'm not a mathematician myself. I'm not very deep into this.
I hate math.
Sorry?
I hate math.
Yeah, I mean, probably we all are of this kind because we are engineers. So, and for engineers, the math is, you know, it's not the goal of life. The math is a tool to do something that you can test on a real system, right?
Yes.
So that's what I do. I honestly sometimes don't even think, like, as long as I'm able to apply some procedure to get some numbers that make sense, so I'm happy with that. So probably you will be too. Okay, so what we have to do next? Yeah, this is by the way the case for MATLAB. That's nice because now, of course, imagine that this was relatively simple for us to do. So imagine MATLAB did it very fast for us and we got the same result, but we could have done it quite easily before by hand. But imagine you have a complex case of complex roots, and then things like that pop up. See, we have now one number is Okay, I don't want this thing to happen. Okay, you have these roots here, complex numbers, see? I stands for the imaginary part, and as well here, a couple of numbers here. So if you, so the solution will be like this. The solution will be like this. And then that's why I deliberately wanted to skip this part, because it's really much more involved than the previous case, okay? But the good thing about is that we have our friend MATLAB, which will do this nightmare of partial fraction expansion for us, so we are safe. But even though in all textbooks people are required to be able to do the procedure by hand, at least for the real numbers like this. So I also will want you to do this procedure for the homework problem, so that you make sure you understand how to do it. Just like for the kids at school, the teachers require students to know how to do the arithmetics on.
How big is this homework?
Right?
How big is this homework?
Okay, we will go back to this quickly, actually. So I can show you right away. So this will be the suggested problem, okay? So it looks a bit differently, because actually we are given a difference equation as the input. See? Remember, this looks like a difference equation. So we have our output, right? We have output, which is one step shifted in time. So basically, as we say it in colloquial terms, imagine that n is today, n minus 1 would be yesterday, and n minus 2 would be 2 days before. So the day before yesterday, right? If we use time index as day, right? So this looks like a difference equation. Imagine you need to find you need to solve it, meaning solving the equation means that you write what is y as a function of n. So in order to say that, you have to solve it, right? And you need initial conditions. Otherwise, you will not be able to get the solution. So we still need to go back to a few more slides with the example. And you will see that to solve this equation using the Z-transform method, you will have to do the partial fraction expansion anyway. So that's why we are learning it, right? And imagine what you'd expect to have here. The answer you are also given at the back of our textbook. This will be the intermediate answer with the Z-transforms, and applying the entries from the table, we will get the answer this. So you will validate your answer. So this will be your problem, and this will be your solution. So I will ask you to do this to validate the solution by hand, so you get these numbers on your own. Okay? You have to be able to develop these numbers here, and this is for you to check that you are on the right track.
So which part are we doing by hand?
Well, basically, I will ask you to do everything by hand here. Okay? Just like
Right.
as we using the example. So yeah, everything by hand in this particular example. Once you know how to do it by hand, we will revert to MATLAB functions, just not to waste our time, because we will have more important goals in front of us in the next lectures. But in this particular lecture, since we learned the Z-transform, we have first to know how to use it by hand. You know the mechanism, and then we will revert to MATLAB whenever it's possible. Okay? Okay, so we still need to do some exercise to make sure that we understand the pattern here. Okay, we skip these for the time being. Yeah. Here, just probably 2 slides from the theory on how you solve difference equation using the Z-transform. Apart from using the lookup table, we have to use another important property of the Z-transform, the shift property. The shift property tells us that For instance, if you want to calculate the Z transform of your output, which is shifted in time by 1 unit, this will be equivalent to applying the definition of the Z transform like this, right? Imagine that, which is simply using the definition of Z transform, only instead of y as a function of n, we place y as a function of n minus 1, meaning that we have a shifted version of our output. Now, if you expand this expression by substituting the powers of n, meaning, for instance, if you substitute n equals to 0 into this, we get y in the brackets minus 1, because 0 minus 1 is just minus 1, right? And you recognize this as what? This is the initial condition. Some number given to us in the problem statement, right? Because we have to know what was the situation with the system before time 0, right? We have to have some initial data, otherwise we are not able to move from the starting point, right? Then we substitute n equals to 1 into the equation, we get y as 0, right? And z raised to the power of minus 1, etc. Now, what we can do here, we can put z raised to the power of minus 1 in front of the brackets, because we can always have terms expressed like that, right? So we leave this number alone in front, of course, there's nothing we can do about it, and we put z raised to the power of minus 1 in front of the brackets. Then we rearrange terms, and if you're careful, you look at these brackets, and this is simply nothing else but the expression of the Z transform for our output, right? This is our output. So we place it back to the compact form. So after we do that, we observe that the conclusion is, if you want to know what is the Z transform of the output shifted by one sample, you have to multiply its Z transform by this, plus add the initial condition. So this is the case for the shifting by 1 unit. Imagine if you want to shift it by 2 units. So now you have to make the same derivation. Now, the second initial condition will pop up, of course, right? If you place 0 here, you will have y minus 2. And you have accordingly all this expression. Now you place z minus 2 in front, because this was minus 2, so you place minus 2 in front. Again, you recollect terms, and you have yz here, but apart from that, you have 2 additional terms. So each time you shift your output by 1 unit to the right, you will get additional term in the expression. It becomes a long, imagine if you have a case with many terms, like m terms, right? If you want to shift it by m units in time, then your last expression will be according number of terms in front of the main function yz, right? So we have a long string of initial conditions here. These are all initial conditions. Well, the good news that when we solve problems, I usually revert to the lower numbers. So we don't use long strings. We say first order system and second order system is our goal. We don't go into the m order system with many numbers, because then it would be a very complicated, long writing. Okay. Then we revert usually to software to do the solution for that.
Can we shift it to the left?
Sorry?
Can we shift it to the left?
Yes, of course we could do that. The formula will allow us to do, but the point is we don't want to design systems that you cannot implement in physical, because shifting to the left means you want to advance the signal. So basically you want to design the system which will not work in real time, because time only moves forward, right? We can only delay things physically. We cannot advance things, because that will violate the the flowing of time, right? So that's why we usually talk about shifting to the right, because it means that this is that we can do with real system. Even though the mathematical apparatus is just good for doing this, the opposite thing. You can advance signals perfectly. You can place ones in here and then it will work. Yeah. Okay. Now we have two examples how we do the procedure, and that's exactly the examples that you have to you will want to use to solve this your homework, right? Okay. By the way, this is the procedure. This is another procedure that we will be using, right? So let's look first at the text. Step number one will be we apply Z transform to the difference equation. So in other words, we convert from time domain to the Z domain. Then we substitute the initial conditions given to us usually in the problem statement. Solve the equation in Z transform domain. And since we need to come back to the time domain, we have to apply the inverse Z transform using our lookup table. And this point we already covered in the previous example. So the new points are only the beginning here, right? Okay, let's do that. Here's the equation. So something similar that you will have in your homework. This is the difference equation, which describes our DSP system, right? Since this is a first order equation, meaning that our shift in time is only 1, n minus 1, no more. So we need only one initial condition. Imagine that somebody told us that it is just this, okay? Okay, we do step number one. We apply Z transform to the equation. It's quite simple, as you will see. So yn turns yz. 0.5 minus is still there, the same. Now, remember, shifting by 1 unit means yz times z squared to minus 1. If you see this, it means that this corresponds to the shifting by 1 unit. Time domain, z domain. But be careful, don't lose the initial condition. Sometimes it's tempting to write only this and forget about this, but we have to use the initial condition because that's what our procedure tells us here. Look at this part. Look at this part and you will see what I mean. This one. Don't lose this one. It's a common mistake that students do. They just forget about initial condition. It's still there. Now, what do we have? So this is for the left-hand side. Now we look at the right-hand side. Right-hand side is 5. And we need to Z transform the remaining thing. Okay, we rewrite it for the time being. Z transform of everything in the bracket. Now, we go to the step number 2, substitute the initial conditions. In our case, we only have singular condition, right? So this one. So we rewrite yz minus 0.5 brackets. Instead of this term, we write number 1 plus rewrite this one equals to 5. And now we observe, we remember this one? This is our familiar thing already. This is the number raised to the power of n. It has the function z divided by z minus 0.2. Just if you forgot it, this one. We look at this table. We look at this table here. Line number 6. Line number 6. We have our term, this one, and its Z transform is this one. So A is 0.5 in our case, right? Okay, it means that, sorry, 0.2 in our case. So we change this thing in the brackets by Z divided by Z minus 0.2. And don't forget that you still need to multiply it by the constant, which was 5 here, right? So we transformed the right-hand side. That was also simple procedure. Now we would do what? We need to do some simplification. So we multiply the number 1 by 0.5, this one by 0.5 as well. Now we put things that have YZ next to them in the left-hand side, and all the other things go to the right-hand side. Now we need, we need to take the common denominator for these two. After we do that, we get this expression, right? So we need, since this doesn't have any denominator, so we have to find the common denominator and to group terms. So after you do the maths, this is what pops up here, okay? I believe you follow this part, are you? No complications here?
No, not yet.
I believe you should be able to replicate these things. If you don't have enough time, of course, just study at home. Study this example. There shouldn't be any catches here. I believe it should be fine. Then what we have here? We arrive at the situation. Yeah. Now we have to write what is YZ. So you basically have to rearrange things, and you got this one, right? After rearranging. Remember, our procedure requires, now we are about to apply things that we already know to get to the partial fraction expansion. So first of all, remember, we have to get rid of negative power of z. So we have to multiply everything by z. If you had -2, you would have to multiply everything by z squared. But this time we only have z raised to the power of -1, so z is enough. Z at the numerator, Z at the denominator. After you multiply Z by the first brackets, you get rid of the negative power. Okay, that's the end result. Now, again, remember, for the second part, step number 2 in the partial fraction expansion algorithm, you have to divide by Z to get Z here at the bottom, right, on the left-hand side. So then you get rid of Z here. You get rid of Z here, and you don't see it here anymore, right? It's because now it's here. So now we're ready to go. Again, we have 2 terms, so A and B. If you had 3 brackets, you would have C, third term. Now you have only 2. Again, the same procedure. Mapping, this mysterious thing that we have a puzzling here part, but if you arrive to this part, and substitute corresponding numbers, you will have easy things to do. You have 2 numbers again, 8.8 and -3.3 for B. Okay. Again, you have to multiply then by Z. We borrowed Z here, and now we have to put it back. So we place Z here and Z here. Okay. And this is again last step. Using lookup table to come back to the time domain, our familiar thing, 0.5 raised to the power of n and 0.2 raised to the power of n. See? So basically, things repeat here already several times.
Excuse me.
Sorry, could you explain again what's the relation between like the difference equation and what's it, the transform? It's like, why do we need it?
Okay, is it the same as you think? Why do we need to do this? Why cannot we solve this equation right away in the time domain? Or I'm not sure if I understood the question.
Yeah, yeah, that's it.
Yeah, okay, this is if there are two things actually. One is historic reason. So when people did not have computers, solving differential equations of a difference equation by hand was a very tedious task. I mean, it wouldn't be very tedious for the first order system like we have in this example. But imagine if you have powers of z which are more than -2, -3, -4. Well, just answer the question. Have you ever tried to solve the equation which is not quadratic but of the cubic form? Cubic equation. Have you ever tried it by hand?
No.
You will know what I mean. That's a nightmare. That's why it's possible to do it, but unless you are a true mathematician, you will be real upset if you have to do it. And that's the point, that if you want to handle this thing by hand or high order systems in time domain, you are lost, you are dead, no? But if you use the Z transform, you do it by divide and conquer. You can expand any big size fraction into small pieces, and you can apply A, B, C, D, E, no matter how many of those. And so by this you can arrive to the solution in reasonable course, you know. That's why you can do it. Because imagine if you want to place a big chunk in your mind and do it directly without resolving to Z transform, you will be dead, you know? So that's the historic reason. Of course, nowadays, when we have computers around, we have software routines that will allow us to solve difference equation in just a fraction of a second, you know? So we wouldn't be bothering with that. However, there's another reason which still persists to today. So we don't result only to historical reasons. Another reason why we need the Z transform will become clear to you when we go to chapters 7 and 8, which deal directly with implementation of digital filters. And here we will see that there will be several stages when you design a digital filter. One stage will be a mathematical one when you play with formulas, but the last stage will be when you have physically to design the filter, to implement it using your mathematical solution. So then you will have to find and you will see that implementation is done using the Z transforms. So in any case, you have to have your system described in Z transform terms, because you will have at the very end you will have to implement it as an engineer. So that's why importance of learning Z transform. It's not only for historical reasons, but it's also because we have to implement the system, which are which are always written in Z transform. Well, unfortunately, I am not prepared to explain to you any clearer, because it's the topic of coming lectures actually still. For the time being, I just want you to know that these things that we are studying here, it's not just to make you busy with your brains here, to do one more math exercise, but it's actually, they have applicability, they have application here in engineering problems, in particular with design implementation of digital filters. Okay, then, did I answer the question?
Yes.
Okay, so we just have to rely on this. It's important, believe me, it's important. And I just, yeah, what time is it? Is it okay, 11:30? Okay, we still have some time.
Could you show us the last slide where is homework? I would like to rewrite it.
Oh, you're doing this?
I would like to. Could you show the last, no, the one before? Yes. Will you upload the slides though?
Yes, actually, I will place these slides just into the Zoom. Yeah, our lecture there. So you, oh, sorry, not to the Moodle. Yeah, I will place it to the Moodle next to the previous presentation. So you will find the slides. So you don't need to rewrite them right away, I believe. You will find them there. So my strongest suggestion is you do the problem. Do the problem. And, well, actually, I will probably just... I should place this problem as a homework, as a formal homework, because you are supposed to have this homework as a separate grade, even though, since most people chosen already to do the presentation, and some people already did the presentation of slides, and other people will be doing presentation of slides, right? So I promise to you that I will give you points for these presentations. So basically, the problem is solved with the homework. But anyway, I believe that would be a good thing for you to do it. I mean, just practice, because you have to you have to practice this. If you don't try it on your own, things will not be clear. So I strongly suggest that you do the problem and get these numbers. I tried it myself. It worked. I checked it. So it's the right solution here.
Could you move to the last slide for a few seconds? Thank you.
Excuse me, Professor.
Yeah.
Did you already send the homework, or you still didn't send it to us?
I couldn't hear you. Could you make it louder a bit?
I'm asking, did you already send us the homework or not yet?
No, I didn't send it the homework yet. My intention is I will put it on the Moodle together with the slides, maybe today or tomorrow. So I will put it. I put the slides here and we put the assignment as a homework.
And
But
how can I
actually-
find the link to this lecture? Because I couldn't find it on Moodle, and I sent an email to ask for the link.
He will upload it, he said.
I will.
Link-
it's not there. I will do it
to the
after the
lecture.
lecture. Yeah, it's not there at the moment, but I will do it just shortly afterwards. Yeah.
يعمل حجمة تفهم.
Okay, thank you.
Yeah, I'm not asking
Okay.
about the homework, Professor. I'm asking about the link that will lead us to the lecture later. Can you put it in Moodle, please? Because I couldn't find the link when I was searching for this lecture.
But you did get. I'm not quite understand if I. You did
The
get the
link-
Zoom the invitation to this lecture on the Zoom, right?
No, I didn't
One
get
of my
it, by the way.
Yeah, one of my friends just sent it to me on Messenger. I didn't.
Yeah,
get
me
the-
too.
Oh, that's interesting, because I assumed that you all have your student. You all are using VGTU mail address, right?
Yeah, we
Yeah,
are
I'm
using it.
using VGTU
So
email
you
address,
should
but
be
I didn't receive your email.
assigned. Okay, could you please then, because I just send me by email people that do not get messages from me. So I will check what's going on there, because I assume that you all are enrolled in my course. So you should. I assume that you get messages from the Moodle automatically.
I got like an email from you during a plan during quarantine where you gave us where we can find
Because
for more
actually I'm
details.
sending. Each time before our lecture on Zoom, I send you an invitation to join the lecture on Zoom. So if you, in case you don't receive this, so send me an email so that I know how many people do not get messages. Okay.
Okay, I'll send you hi.
And then I will try to somehow to maybe I need to in the Moodle to put your name somewhere. So because I thought that you all get these messages, but okay.
This is good.
So I believe we still have one more example relevant to our homework, because this was example 513, and we covered that. And there's one more. There's one more which is yeah, just the same, of the same shape. Only the difference equation involves not only y and its shifted versions by 1 and by 2, for instance, but also it's a more involved case when we have input, which is also could be shifted in time, for instance, by 1 unit. So basically, a difference equation is one that you have your output shifted by 1 more time, and current input value, and a previous input value. So this equation looks like a more involved case, but we have one simplification where we have a relaxed system, so to say, where a relaxed system means that we have 0 initial conditions, as opposed to the previous case where we had non-zero initial conditions. See, it was 1, not 0. Now we have a situation when we have all 0 initial conditions. So But of course, this recipe of solving it will be similar. There's nothing new here. So, but we are asked to do two things: to determine the impulse response. Okay, imagine that you have to find what is the output. Then we have a particular input, and input is our delta function. So imagine that you place delta function instead of x. X could be any function, right? It's a general expression. So in our particular case, we will substitute delta function for x here in both cases, right? In part A. And in part B, we want to do the same by inputting unit step, right? Unit step function. So delta function and unit step function as our input. Okay. So first we do part A. Again, this step should be clear. We transform it to Z domain, Y, Z, 0, 1. Since we are given 0 initial conditions, so we only have a simple YZ times Z raised to the power of -1 because we have -1 here, right? So if -2, we have -2 here. Quite simple, right? Simple transformation. When xn turns to xz, and since we have a shift, you have to have z raised to the power of -1. So both for the input and for the output, we do the same procedure. Again, doing some maths, factoring yz in front, all the terms that have yz, we factor them out. So we get 3 terms on the left-hand side, and on the right-hand side, we have this. Observe also that since our input is delta function, and we know from the table that the Z transform of delta function is nothing else but unity. So we place 1 instead of xz. We place just 1. So it doesn't make sense you multiply 1 by something, but we deliberately do 1 to show us that this is the Z transform of delta function. So this unity corresponds to the Z transform of delta function. And since we have 2 terms, we have 1 plus Z raised to the power of -1. Okay? Then we need to express YZ. So simply rearranging terms, we get the fraction. Again, we have to get rid of negative powers of z, so we have to multiply numerator and denominator by z squared, right? This is what results. And now we know that we can split this polynomial into 2 parts like this, okay? And we are ready to go with the partial fraction expansion, but don't forget to divide yz by z. So that's why we get rid of z here, right? Again, AB, same mystical procedure, blah, blah, and we get these numbers, right? Which gives us the impulse response. So this is the output, how our system responds to the output. Well, if you want to make sure if you did the right solution, solve the equation. Place, for instance, instead of n, place 0 and calculate what comes out. Then place 1, calculate what comes out, and go back to this expression, put these numbers into it, and you should have the right equality. If this is the case, if you for 2 steps, actually for 3 steps, because 0, 1, and 2, 3 steps. For 3 steps, if you have equality, it means that you got the right solution here. You got the right. That's the way manually to check if you did the right solution. Just as for any regular equation, substitute numbers and check if you get the equation right. If equality does not apply, meaning it means that you made a mistake somewhere in your arithmetics or algebra or whatever, right? Go back to some stage where you did a mistake. Okay, number 2, part B. We want to do the same now. This time we apply, instead of x, we apply unit step. So Now, instead of 1, we have, remember, the unit step has a Z transform of this. This we take from the table, from the lookup table. And that's why this term pops up in front. So we have the same expression as before, only instead of 1, because here we already had this one. Look, this was here. This was here. But now our input is not delta function, but our input is unit step. So that's why we have extra term in front of the big brackets. This is the Z transform of the unit step. That's why our solution now involves 3 terms, and that's why we will have A, B, C now. We will have A, B, C, and I don't replicate the procedure, I just give you the result. So we have A, B, C, these numbers. So, see, that's the power of Z transform method, that you can extend it to any number of terms without, of course, it will mean that you will have to, the number of calculations will go in proportion to you, but then the complexity of the problem will not, as opposed to your attempt to try to solve the equation in time. Just as I told you, try to solve the cubic equation and you will see what I mean. It's because the complexity of the problem grows exponentially. And here the complexity of a problem doesn't grow exponentially, it simply goes linearly, in linear fashion. You simply have to do one more calculation for C constant. Okay. And then this is the homework. Okay, I will, since you have the slides, you know that what number it is from the textbook. We still skipped this solution of complex roots, right?
Should we upload the homework, like to send you via email, or you gonna make an upload attachable file in Moodle?
I will do it in Moodle so that you see the deadline, okay? Because I want to make sure that you observe the deadline. So, because otherwise, you know, people start sending you 1 month later. I will give you two weeks deadline, okay? I believe you managed, so say 1 week is not enough for you. So I suppose 2 weeks should be enough to complete the assignment. And then you know that if I place it on, I never used Moodle for this particular purpose, but I believe things should be working fine. Nothing. I read the instructions, what is there, and some probably it should be easy. So then I will place the assignment. You will see the deadline for 2 weeks, and I hope that you deliver me your solutions just by Moodle, through Moodle.
All right.
Okay. And this is when the case of a complex roots. You will have to do some solution with the, especially this part, right? You have to know how to convert, actually you know it, you have to convert from rectangular form to the polar form, like absolute value and phase angle. Well, honestly, I don't want you to bother with this, you know. I will be happy if you know how to do it just with real poles and real numbers. Because our homework will involve, as you see here from the answer, this will be just regular numbers, no complex numbers, right? So probably, yeah, we can just stop this lecture because I might need like half an hour extra to explain you the complex root case because it's a long one, right? Yeah. It's all, we have to observe the phase angle because depending on the sign of the real part and imaginary part, we have 3 cases. So this is a separate note for the determining the angle. If to add 800 degrees or to extract or subtract 800 degrees from the phase angle. So it's something which is arithmetics of a complex number. Yeah. It's the same thing, same principle, but you have to use complex numbers.
So we are done for today?
Well, I believe, yeah, my intention was to explain you this example as well, but I see we are running out of time because it's almost 12 o'clock and we didn't have any break. So So we have used all our time for today. So I believe I should skip this example. And I'm honest with you, I will not be giving you the assignment with complex numbers from chapter 5, so as a homework. So probably you will not be very angry at me if we skip this example. Do we have any? So wait a minute. Do we have any chats? Did anybody write me there any messages? I didn't check yet. Wait a minute. I just stop sharing the screen and I check the chat. Okay, the test. Yeah, I have the answer, the question from Francisco.